inside a patch of sky that looks almost empty. James Webb found the universe behaving as if it already had a skeleton. Not a wall you could fly toward, not a glowing object with a sharp edge, not a single monster drifting through space. What Webb revealed is quieter. Ancient galaxies arranged along invisible threads, separated by dark voids, inside a structure no human eye could recognize from one point of view. To us, the night sky looks scattered, a star here, a galaxy there, a black gap between them. But when an infrared telescope stares long enough, and when thousands upon thousands of faint galaxies are placed at true distances, the darkness begins to organize itself. Points become chains, chains become filaments. Filaments meet in knots where galaxies grow faster, burn brighter, and sometimes die earlier. Empty regions are the spaces that give the web its shape. That is the real pressure inside the title. James Webb did not take a photograph of physics breaking. It did something more useful. It gave astronomers a sharper way to map the cosmic web, the largest architecture in the known universe, and to ask whether some of its early structure appeared sooner, denser, and more organized than our simplest picture would have expected. And the uncomfortable part is not only size. Size alone can mislead us. The universe is allowed to be enormous. Gravity is allowed to gather matter. Dark matter is allowed to form invisible scaffolding. Over billions of years, small differences can become vast arrangements. But time is the harder question. If a structure looks mature when the universe was still young, if dense regions already seem to be shaping galaxies before the cosmic story has had much time to unfold, then the problem is no longer just how big the structure is. The problem is how quickly the universe learnt to build it. Before we go deeper, if you enjoy calm science stories that separate real mystery from fake certainty, stay with this one and tell me in the comments which idea feels stranger to you. A universe that is mostly empty, or a universe whose emptiness is threaded with hidden order? Because the hidden order is where the story begins. Imagine holding a grain of sand at arm's length against the sky. Behind that tiny patch, there are galaxies whose light has been travelling for most of cosmic history. Some of that light began its journey before Earth existed, before the sun formed, before the atoms in your bones had been gathered into a planet. By the time it reaches a telescope near Earth, it has been stretched by the expansion of space into infrared wavelengths, too red and too faint for human eyes. That is why Webb matters. Its gold-coated mirror and infrared instruments are tuned to light stretched across time. A young blue galaxy in the early universe may arrive to us as a faint red smudge. A cluster may reveal itself not only through the galaxies we can see, but through the way its gravity bends the light of galaxies behind it. A broad field of faint dots may become a map if astronomers can estimate how far away each dot is and where it belongs in cosmic time. That last part is crucial. A deep image by itself is not yet a structure. A flat picture can fool the mind. Two galaxies may appear close together on the sky, while actually being separated by billions of light years. A real cosmic map requires distance. It requires redshift. It requires sorting the foreground from the background, the nearby from the ancient, the accidental alignment from the physical environment. So when astronomers use Webb to trace large-scale structure, they are not simply looking at a dramatic pattern and declaring a discovery. They are collecting light through filters, estimating redshifts, measuring galaxy properties, and rebuilding the three-dimensional arrangement from incomplete clues. The structure is not written on the sky like a drawing. It has to be recovered. And once it is recovered, the familiar picture of space begins to fail. We are used to thinking of gravity as something that pulls objects together. Drop a stone, and it falls. Let a planet orbit, and it follows a curve. But on cosmic scales, gravity is not just a pull between things, it is a slow editor of the entire universe. It takes tiny differences in density, almost invisible at the beginning, and gives them time. The slightly denser regions pull in more matter. The emptier regions lose matter. The difference grows. What began as a whisper becomes a filament. What began as a wrinkle becomes a road. This is the cosmic web, a vast network of galaxies, gas, and dark matter, stretched across distances so large that ordinary language starts to lose its grip. Galaxies are not sprinkled through space like dust. They tend to live along filaments, gather at intersections, and avoid the great voids. Our own Milky Way is not outside this pattern. It belongs to it. We live inside one strand of a structure so large that the strand itself feels like the universe from within. But Webb is pushing that pattern backward. The older and deeper the light, the less time the universe had to build what we are seeing. That is where the tension enters. If dense environments are already influencing galaxy growth when the universe is only a fraction of its current age, then astronomers have to ask whether the early Webb formed more efficiently than expected, whether we are seeing rare peaks of structure, whether our models of galaxy formation need adjustment, or whether the measurements themselves still hide uncertainties. The safest answer is not the loudest one. Physics has not been thrown away. The standard model of cosmology still explains the expansion of the universe, the afterglow of the Big Bang, light element abundances, and the broad statistical pattern of galaxies. A model that successful does not vanish because new data is uncomfortable. But successful models can still be pressured at their edges, and that is what makes Webb's view so powerful. It does not show us a cartoon universe where scientists were simply wrong. It shows a universe whose details are becoming sharper than the old blur allowed. Dense regions are not just background scenery. They may change how galaxies grow, how quickly they build stars, how soon they become massive, and when star formation begins to shut down. The Webb is not passive. It is an environment. It is a machine made of gravity, dark matter, gas, heat, time, and chance. If you could step outside the visible universe and see the whole pattern at once, it might not look like a collection of galaxies at all. It might look like foam, or frost spreading across glass, or a nervous system made of light. But every glowing point in that image would be real matter. Every dark gap would be a history of matter flowing away. Every dense knot would be a place where gravity kept winning. And somewhere in those knots lies the reason the title feels dangerous. A structure does not need to violate physics to challenge us. It only needs to form earlier than our intuition expected, concentrate more strongly than our models predicted, or reveal a pattern before we understand how the pattern became so clean. The universe may not be breaking its rules. It may be showing us that we understood the rules too simply. That difference matters because once Webb turns darkness into a map, the question is no longer whether the universe has a skeleton. The question is how much of that skeleton was already there when the universe was still learning how to shine. The first mistake is to imagine the early universe as empty space waiting for galaxies to appear. It was never empty in that way. Even before the first stars switched on, the universe already carried a pattern. Not a visible pattern, not a pattern made of shining things, but a difference in density so small that it would have seemed almost meaningless. One region held slightly more matter than another. Another region held slightly less. The differences were tiny, But gravity is patient. It does not need a dramatic beginning. It only needs an imbalance that survives. Those first imbalances are preserved in the oldest light we can see, the cosmic microwave background, the cooled afterglow of the hot early universe. In that light, the temperature variations are only about 1 part in 100,000. To human intuition, that sounds too small to matter. A room warmer by that fraction would feel identical, but across the whole young universe, those tiny differences were the seeds of everything later built. This is where ordinary thinking breaks. We expect large structures to require large beginnings. Mountains need tectonic violence. Cities need roads, workers, materials, plans. A galaxy cluster seems as if it should need a huge initial shove, some enormous cosmic event powerful enough to gather thousands of galaxies into one gravitational region. But the universe did not build structure like a machine starting from parts. It grew structure like frost grows on glass, from small irregularities, amplified over time, guided by conditions already present. Dark matter was the first invisible advantage. Ordinary matter, the matter that makes stars, planets, dust, gas, and bodies, could not immediately collapse into galaxies after the Big Bang. For hundreds of thousands of years, it was tangled with radiation in a hot plasma. Light kept pushing on charged particles. Pressure resisted collapse. The universe had matter, but ordinary matter was still not free to fall cleanly into dense clumps. Dark matter behaved differently. It did not shine, did not absorb light, and did not feel radiation pressure in the same way. It could begin gathering under gravity earlier, forming invisible wells before the first galaxies became visible. When ordinary matter finally cooled enough to move more freely, it did not enter a blank universe. It fell into a hidden landscape that dark matter had already started to carve. That is why the cosmic web is not simply a web of galaxies. The galaxies are the lamps. Dark matter is the road system underneath them. When James Webb sees faint galaxies arranged in dense regions, it is seeing the luminous trace of a deeper structure. The telescope is not detecting dark matter directly. It is detecting the places where ordinary matter has responded to gravity. It sees starlight, colors, and redshifted infrared glow. From those signals, astronomers infer the environments where matter has gathered. The brightest features may be only the visible edge of something much heavier. This is why a structure can be larger than it first appears. The galaxies are only the beads. The gravitational thread runs through and around them. If you counted only what glows, you would miss the mass that controls the arrangement. If you looked only at one image, you might mistake a deep structure for a random scatter. The true map requires distance, density, and the invisible pull that organizes both. Now the title becomes more precise. The problem is not that physics has a rule saying no structure may become enormous. Physics allows gravity to amplify small differences. It allows dark matter halos to merge. It allows clusters to grow at the intersections where matter streams inward from several directions. What physics constrains is probability, timing, and growth rate. Given the age of the universe at a certain redshift, given the amount of matter, given the expansion rate, how often should a structure of a certain density and scale appear? That is where discomfort can begin. A single large object may be rare, but allowed. A dense galaxy environment may be surprising, but not impossible. A massive cluster at early times may sit in the tail of what simulations predict. But if surveys keep finding systems that are too mature, too concentrated, or too organized too early, the question changes from, can this happen, to, why does it seem to happen this efficiently? This distinction is the difference between fake crisis and real science. Fake crisis says the universe broke physics. Real science asks what assumption is being tested. Was the initial density field slightly different in the relevant region? Are we seeing an unusually rare peak? Did galaxies form stars more efficiently in dense environments than our models allowed? Did feedback from supernovae and black holes behave differently in the early universe? Are redshifts or masses being overestimated? Are simulations missing small-scale physics that matters more than expected? To understand the pressure, picture the early universe not as a flat stage, but as a landscape in the dark. Some places are shallow basins, some are deeper valleys. Matter flows toward the deeper regions, not because it knows where to go, but because gravity makes some paths easier than others. Over time, galaxies form first in the densest wells. Then those galaxies merge, feed, heat their gas, and influence the next generation of growth around them. The environment starts to matter before the environment is visible. A galaxy in a dense region does not live the same life as a galaxy in isolation. It has more neighbors. It may merge more often. Its gas supply may be disturbed. Its star formation may ignite rapidly and then fade. Its central black hole may grow by feeding on gas driven inward by interactions. The larger structure is not just a background map. It changes what the galaxies become. So when Webb helps trace early dense environments, the telescope is also tracing the beginning of cosmic inequality. Some regions of the universe became crowded early, others remained quiet. Some galaxies grew inside crowded knots where matter arrived from many directions. Others lived along thinner filaments, or in quieter regions. The cosmic web did not merely contain galaxies, it assigned them different histories. And this is why time becomes the real measure of strangeness. 1 billion years sounds long because it is longer than any human civilization, longer than complex life has existed on land, longer than mountains can rise and erode. But for the universe to build massive galaxies, clusters, and large environments, 1 billion years can be a narrow window. Gas has to cool, stars have to form, heavy elements have to be produced, dark matter halos have to merge. Nothing happens instantly, even when gravity is always working. That is why early structure carries pressure. It compresses the story. If a dense environment appears when the universe is young, every step before it has less time to occur. The initial dark matter peak had to be strong enough, gas had to fall in efficiently, star formation had to begin quickly, galaxies had to become visible enough for Webb to detect. If the region is massive or strongly connected to surrounding filaments, the sequence becomes even tighter. The question is no longer whether gravity can build a web. It can. The question is whether the web we are beginning to map formed with the timing, density, and efficiency our models expect. And the next layer of the story is even more delicate, because Webb does not simply hand us the answer. It gives us ancient light, stretched into infrared, filtered through distance, dust, selection effects, and uncertainty. To turn that light into a structure, astronomers have to ask not only what they are seeing, but how they know it belongs together. That is where the discovery becomes less like a photograph and more like an argument built from light. A telescope does not look at the early universe and see a label attached to each galaxy. It does not receive a clean message saying, this object is close, this one is ancient, this group belongs together, this one is only an accidental overlap. The universe sends photons. Everything else has to be earned. A photon leaving a young galaxy begins its journey with a certain wavelength, perhaps ultraviolet light from hot newborn stars, perhaps visible light from older stellar populations, perhaps emission from gas excited by radiation. Then, space expands while the photon travels. The wavelength stretches. What began as blue or ultraviolet light may arrive billions of years later as infrared. Webb was built for that kind of ancient, tired light. Its detectors are waiting in the range where early galaxies have been shifted by cosmic expansion. But color alone is not enough. A red object may be far away, or dusty, or old, or some mixture of all three. A faint object may be distant, or small, or hidden by dust, or simply not forming many stars. A galaxy's apparent brightness is not a simple ruler. To turn a dot into a place in cosmic history, astronomers compare its light across multiple filters. They ask where the spectral break may be, how much light disappears in one wavelength range and appears in another, and which model of a galaxy best matches the observed pattern. This is called photometric redshift, when it is estimated from colors rather than from a precise spectrum. It is powerful because it can be applied to enormous numbers of galaxies. It is also imperfect because many different galaxy properties can imitate each other. Dust can redden light. Age can redden light. Distance can redden light. A galaxy with strong emission lines can make one filter brighter than expected. The result is not a single unquestionable number, but a probability. This galaxy is most likely at this redshift, with this range of uncertainty. That uncertainty matters because a structure is made from positions. If a group of galaxies appears close on the sky, but their redshifts are different, the group may not be real. It may be a projection, a trick of perspective. If their redshifts cluster together, and if many galaxies occupy the same region of space and time, the pattern becomes harder to dismiss. The structure begins to rise out of the data. This is one reason Webb's deep surveys are so important. They do not merely find the most distant galaxy candidates, they help fill in the environment around them. A single galaxy can be spectacular, but an environment tells a different story. It shows whether that galaxy is alone, whether it lives in a dense knot, whether it sits along a filament, whether surrounding galaxies share a similar epoch. The cosmic web is not identified by one bright object. It is identified by relationships. The evidence path is slow, but it is the only way to make the title honest. First comes the infrared image, then the catalogue of sources, then the measurement of colors, then the redshift estimates, then the mapping of where galaxies fall in three-dimensional space, then the density calculation. Where are galaxies more crowded than average? Where are they sparse? Where do connected regions appear? Only after all that can astronomers begin to speak about structure. And even then, the correct word is not certainty, it is confidence. A dense region in a Webb survey is not the same kind of evidence as a rock in your hand. You cannot touch it. You cannot send a spacecraft across it. You are reconstructing it from light that has crossed billions of years of expanding space. Every distance estimate carries uncertainty. Every sample is shaped by what the telescope can detect. Fainter galaxies may be missing. Dusty galaxies may be undercounted. Some redshifts may later be corrected by spectroscopy. But uncertainty does not make the structure imaginary. It defines the boundary of what we can responsibly say. This is how real science becomes more gripping than hype. The measurement is not magical. It is fragile, but it is not empty. It survives because many faint signals, placed together, begin to form a pattern stronger than any one galaxy alone. A single dot can lie. A population is harder to ignore. Think of standing in a dark valley at night with only a few lamps visible on distant hills. If you see 3 lamps, you cannot map the road. If you see 3,000, and you know roughly how far each one is, the invisible roads begin to reveal themselves. You do not see the pavement, you infer it from where the lights gather, where they curve, where they avoid empty ground. Webb does something like that with ancient galaxies. The lamps are galaxies. The roads are filaments. The empty ground is the void. The hills underneath are dark matter wells. And the question is whether some of those roads seem too developed for the cosmic hour in which we are seeing them. That is why the word found needs care. Webb found light. Webb found galaxies. Webb found patterns in galaxy distribution when combined with redshift estimates and survey analysis. The structure is not a single photographed object. It is a reconstruction, a statistical shape emerging from many measurements. If the reconstruction is strong enough, it becomes evidence for the underlying cosmic web at that time. This distinction makes the story stronger, not weaker. If the title were only claiming that Webb saw a giant thing, the mystery would be shallow. A giant thing can be imagined. It can be drawn on a thumbnail. But the deeper reality is more unsettling. The largest structures in the universe are not objects in the usual sense. They are patterns of probability made physical by gravity. They are regions where matter became slightly more common, where galaxies formed more easily, where space itself seems to carry a memory of its first unevenness. And that memory has to be measured indirectly. Spectroscopy can sharpen the picture. Instead of estimating redshift from broad colours, astronomers can spread a galaxy's light into a spectrum and look for specific features. Emission lines from hydrogen or oxygen, absorption breaks from stellar populations, wavelength patterns that reveal how much the light has been stretched. Spectroscopic redshifts are usually more precise, but they are harder to obtain for huge numbers of faint galaxies. Photometry gives breadth. Spectroscopy gives precision. A world-class map needs both. This is one of the quiet tensions inside Webb's discoveries. The telescope can see deeply enough to reveal faint early structure, but seeing deeply also means working with objects that are difficult to measure perfectly. The farther back we look, the more powerful the evidence becomes, and the more delicate the interpretation becomes. It is like reading a message written on glass after the glass has been stretched across the sky. So the honest question is not, did Webb prove that physics failed? It did not. The honest question is sharper. When ancient light is sorted carefully enough, do the galaxies fall into structures that seem too rich, too connected, or too mature for the time available? If yes, the pressure does not land on one image. It lands on the whole chain, how dark matter clustered, how gas cooled, how galaxies lit up, how environments formed, how quickly dense regions became engines of growth. And once the evidence path is clear, the structure stops being a vague cosmic monster. It becomes something more precise, a test of how gravity turned the early universe from a nearly smooth fire into a web. A nearly smooth universe should not have become beautiful. At least, not if beauty means visible structure, tangled filaments, crowded knots, and great dark cavities where galaxies are rare. Smoothness should have stayed smooth, unless something gave it direction. Yet the universe we observe is not a fog of galaxies spread evenly in every direction. It is more like a vast, uneven terrain, with matter flowing into valleys and leaving high, empty plains behind. The cosmic web is the name we give to that terrain after gravity has been working for billions of years. It is not a metaphor invented because space looks dramatic. It is a physical arrangement. Galaxies tend to line up along filaments. Filaments intersect at nodes. Nodes can grow into groups and clusters. Between them lie voids, enormous regions where matter is thin and galaxies are sparse. The voids are not failures of the map. They are part of the map. Without them, the filaments would not have shape. This is why a structure in the universe is not like a structure on Earth. A bridge has edges. A cathedral has walls. A mountain has a summit and a base. A cosmic structure may be made from separated galaxies, invisible dark matter, hot gas, and gravitational relationships spread across millions or even hundreds of millions of light years. You cannot fly up to it and touch its surface. From inside, it may feel like ordinary sky. Only when distances are measured and positions are reconstructed does the structure appear. That makes Webb's role stranger than a simple discovery story. The telescope is not standing outside the universe, looking back at the whole web. It is looking through a narrow cone of space and time. Every galaxy in that cone is seen as it was when its light began travelling. The farther one is, the younger the universe appears in that direction. A deep survey is therefore not only a map of space, it is also a layered record of time. Nearer galaxies show a later universe. Fainter, more distant galaxies show an earlier one. The whole image is a stack of different cosmic ages compressed onto one sky. To separate that stack, astronomers use redshift. A galaxy's light is stretched by expansion, and that stretching becomes a timestamp. The larger the redshift, the farther back in time we are usually looking. Once enough galaxies have estimated redshifts, the flat image begins to open. What looked like a random scatter becomes a three-dimensional census. Crowded regions can be compared with average regions. Empty regions can be identified. The web begins to recover its depth. But the web is not traced equally at every time. In the nearby universe, large surveys can map millions of galaxies over huge volumes. The web appears with great clarity, long filaments, rich clusters, and enormous voids. In the early universe, the map is harder. Galaxies are fainter, redshifts are more uncertain. Smaller objects disappear below detection limits. Dust can hide star formation. A deep field may cover only a tiny area of sky. So when Webb reveals signs of structure deep in cosmic time, it is not merely adding detail. It is pushing the web into a region where the map itself becomes difficult. That difficulty is part of the tension. If the early universe already contains strong environments, we are not just seeing galaxies appear, we are seeing geography appear. Some places are already more crowded than others. Some regions already seem better prepared to grow massive galaxies. Some knots may be the ancestors of modern galaxy clusters, places where dark matter wells have already become deep enough to shape the life of everything falling into them. This is where dark matter becomes impossible to ignore. Visible galaxies are only a small fraction of the matter that shapes the web. Most of the gravitational scaffolding is dark. We infer it through its effects. Galaxies orbiting too quickly, clusters holding together with more mass than their stars and gas can explain. Background light bent by gravitational lensing. Simulations that reproduce web-like structure only when dark matter is included. The universe's architecture is therefore built mostly from something we do not see directly. That fact should make the title feel less like exaggeration and more like a problem of translation. Webb can reveal the lamps along the web, but not the full road beneath them. When a dense region appears, the visible galaxies may be only the surface expression of a much deeper mass concentration. If that concentration is present early, the pressure is not only on galaxy formation, it is on the growth of the underlying dark matter structure. Gravity builds from the inside out and from the small upward. In the standard picture, small dark matter halos form first, then merge into larger halos. Galaxies grow inside those halos. Groups merge into clusters. Filaments feed mass into the nodes. This is called hierarchical structure formation. It is not a random pileup. It is a slow, branching history. where the largest systems emerge from many smaller ones over time. So a very early, dense environment raises a timing question. How many mergers had to occur? How much gas had to cool? How quickly did stars form? How fast did feedback heat or expel gas? How many smaller halos had already gathered into a shared gravitational region? None of these steps is impossible by itself. The pressure comes when many of them must happen together, early and efficiently. A human lifetime gives no intuition for this. We experience gravity as something immediate, a fall, a tide, the weight of a body in a chair. Cosmic gravity works more like a memory that strengthens over time. A small advantage in density becomes a larger advantage. A larger advantage draws more matter. More matter deepens the well. The well draws still more. The process is quiet, but relentless. Given enough time, it makes structure look inevitable. The question Webb sharpens is how early inevitability began to look organized. If we see a mature Webb today, that is not surprising. The universe is 13.8 billion years old. Gravity has had almost the entire age of reality to work. But if we trace the Webb backward and find dense patterns when the universe was much younger, then the ordinary story has to become more specific. It is no longer enough to say gravity had time. We must ask how much time, under what conditions, inside which dark matter peaks, with what efficiency of gas cooling and star formation. That is why the structure is not one giant forbidden object. It is a chain of connected questions. How early did the dark scaffolding form? How quickly did galaxies light it up? How soon did dense environments begin changing galaxy evolution? How rare are the most crowded regions Webb can see? Are we looking at exceptional peaks, or signs that our models underestimate the speed of early assembly? The cosmic web turns size into history. Every filament is not just a distance across space. It is a record of matter choosing the same gravitational paths for billions of years. Every void is not just emptiness. It is the absence left behind as matter flowed away. Every knot is not just a cluster of galaxies. It is a place where the universe spent time becoming uneven. And when Webb pushes that unevenness deeper into the past, the next question becomes unavoidable. If the web is the visible outcome of invisible dark matter, then the most important part of the structure may not be the galaxies Webb sees at all, but the hidden mass that made their arrangement possible. The hidden mass is where the story stops being only a map and becomes a test of gravity. And galaxy filament can look delicate because most of what we see is light, faint dots, small smudges, thin chains of galaxies crossing a black background. But gravity does not care about what glows. It cares about mass, and on cosmic scales, most of the mass that shapes galaxy structure is not in stars. It is not in the bright spiral arms, not in the blue star-forming knots, not in the golden centers of old galaxies. It is in dark matter halos, extending far beyond the visible edges. This is why one of the strongest clues does not come from brightness. It comes from distortion. When a massive cluster sits between us and a more distant galaxy, the cluster's gravity bends the path of the background galaxy's light. The effect is called gravitational lensing. It does not require the cluster to shine. It does not require the dark matter to reveal itself directly. Mass curves space-time, and light follows the curve. If the alignment is strong enough, a background galaxy can appear stretched into an arc, multiplied into several images, or smeared around the foreground mass like a reflection warped by invisible glass. That distortion is not decoration. It is a measurement. If Webb sees lensed arcs around a distant cluster, the arcs become a kind of gravitational handwriting. They show that the foreground system is massive enough, concentrated enough, and aligned enough to bend light in a measurable way. Astronomers can model the lens, estimate how much mass must lie inside certain distances, and compare that mass with the galaxies and gas that are visible. Often, the answer is that visible matter is not enough. The cluster must be dominated by dark matter. This matters deeply for early structure. A young-looking cluster with strong lensing is not just a crowded patch of galaxies. It is evidence that a significant gravitational well has already formed. The mass has gathered. The central region is deep enough to bend background light. The structure is not only visible through what it contains, but through what it does to light passing behind it. That is a much harder clue to dismiss. A bright galaxy may be temporarily intense because it is forming stars quickly. A red galaxy may be dusty or old. A crowded field may include projection effects if distances are uncertain. But strong lensing points to mass. It says, whatever the light is doing, there is enough gravity here to reshape the path of photons that began their journey even farther away. This is one reason early massive clusters are so valuable. They sit at the intersection of several questions at once. How much dark matter had gathered by that time? How concentrated was it toward the center? How many galaxies had already fallen in? How much gas had been heated into the surrounding environment? How quickly did smaller systems merge to produce a deeper gravitational basin? Each question tests a different part of the story. If the mass is high, the dark matter assembly had to be efficient. If the concentration is high, the central region may have formed earlier or collapsed more strongly than simple expectations would suggest. If the galaxies inside already show signs of maturity, then ordinary matter has also moved quickly through its own slower sequence. Cooling, star formation, chemical enrichment, feedback, and sometimes shutdown. A cluster is therefore not one clock, it is several clocks running together. The dark matter clock measures gravitational assembly. The galaxy clock measures star formation and mergers. The gas clock measures heating, cooling, and pressure. The black hole clock measures how quickly central engines can grow and regulate their surroundings. If all those clocks seem advanced in a young universe, the pressure is not a single dramatic contradiction. It is a coordination problem. Too many processes may appear to have progressed too far, too soon. This is where the phrase "bigger than physics should allow" becomes both tempting and dangerous. Tempting, because a massive early structure feels like a violation of common sense. We want the universe to build small things first, then larger things later, in a neat order we can visualize. Dangerous, because physics does allow rare early peaks. It allows the densest regions to grow faster than average. It allows our surveys to find exceptional objects precisely because exceptional objects are interesting enough to study. The real question is not whether one cluster can exist. The real question is how often such systems appear, how massive they truly are, and whether their properties match the predicted population. One rare mountain does not disprove the map. A mountain range where none was expected forces the map to be redrawn. That is the kind of pressure Webb can create, not by announcing a broken law, but by improving the evidence until the old uncertainty has less room to hide. A sharper image reveals fainter arcs. Better infrared sensitivity reveals galaxies that older telescopes could miss. More careful modeling turns stretched light into a mass estimate. A wider survey places one cluster inside a larger environment instead of treating it as an isolated curiosity. The object stops being only an object. It becomes a node in a system. From the inside, that node would not look like a glowing web. If you were somehow inside a galaxy cluster, the distances would still feel enormous. Neighbouring galaxies would not crowd the sky like lamps hanging close overhead. Many would be faint smears, separated by dark space. The hot gas between them would be invisible to human eyes. The dark matter would not be visible at all. You might feel, emotionally, that you were in emptiness, but the physics would know otherwise. A galaxy moving through a cluster environment can lose gas as it travels through hot plasma. Its star formation can fade because fuel is stripped away or heated. Its shape can be disturbed by encounters. Its central black hole may be fed by interactions and then push energy back into the surrounding gas. The cluster's mass is not passive. It changes the life of every galaxy inside it. That is why the hidden structure matters more than the visible beauty. A cluster is not a pile of galaxies. It is an ecosystem ruled by gravity. The galaxies are inhabitants. The dark matter halo is the territory. The hot gas is the weather. The filaments are the roads bringing matter in from outside. And time is the pressure that decides whether the whole system should have become so organized already. Webb's deepest contribution is not simply that it sees farther, it sees far enough to make these systems young again. A cluster observed at high redshift is not a cluster as it is now. It is a cluster as it was when the universe was younger. Its light is old because the journey is long. But the scene we receive is early. We are not watching ancient ruins. We are watching construction before the building should look so complete. And the more complete it looks, the more each invisible component begins to matter. The stretched arc behind the cluster is a message from background light. The crowded galaxies are a message from ordinary matter. The inferred halo is a message from dark matter. The dense environment is a message from structure growth. None of them alone says physics has failed. Together, they ask a more difficult question. How did gravity gather so much hidden architecture before the universe had finished becoming familiar? The strange thing about the pressure Webb creates is that it lands on a model that has been remarkably successful. The standard cosmological picture was not invented casually. It is not a guess held together by one telescope image or one dramatic galaxy. It grew from many different kinds of evidence that point toward the same broad story. The universe began hot and dense, expanded, cooled, formed light elements, released the cosmic microwave background, and then allowed gravity to amplify tiny early density variations into galaxies, clusters, filaments, and voids. That picture is often called lambda cold dark matter, or lambda CDM. The name sounds technical, but the core idea is simple enough to feel. Lambda represents dark energy, the component associated with the accelerated expansion of the universe. Cold dark matter represents invisible matter that moves slowly enough, compared with light, to clump under gravity and build structure. Together, they form the background stage on which cosmic history unfolds. And for a long time, the stage worked beautifully. It explained why the cosmic microwave background has tiny temperature variations instead of being perfectly smooth. It explained why galaxies are not evenly sprinkled through space. It explained why clusters form at the intersections of filaments. It explained why simulations, when seeded with early density fluctuations and filled with dark matter, naturally grow web-like structure. It gave cosmologists a universe where gravity has enough time to turn faint irregularities into the enormous architecture we see today. That success is exactly why new pressure matters. If a weak model fails, no one is surprised. But when a strong model begins to show tension at its sharpest edges, the tension becomes valuable. It tells scientists where the model is being tested most severely, Not destroyed, tested. There is a difference. A model can be broadly right, while still incomplete in the details that control the earliest galaxies, the densest peaks, the fastest forming clusters, or the rarest structures. This is where Webb enters with unusual force. It does not merely add another image to an old collection. It reaches into an era where the model's timeline becomes tight. Every massive galaxy, every dense environment, every early cluster candidate has to fit inside a universe that had less time to assemble it. The more ancient the object, the shorter the runway. The deeper Webb looks, the less forgiving the clock becomes. Hierarchical growth. The standard structure formation picture says small systems generally build into larger ones. Small dark matter halos form first, gas falls into them, stars form, halos merge, galaxies merge. Groups grow into clusters. Filaments feed mass toward dense nodes. Over long periods, the architecture becomes grander and more complex. There is nothing wrong with that idea. In fact, it is one of the reasons the cosmic web makes sense at all. But the phrase, over long periods, carries the tension. How long is long enough? If a galaxy is already massive when the universe is young, if a cluster core is already concentrated, if a dense region is already shaping galaxy evolution, then the assembly sequence has to be efficient. Not impossible, efficient. Efficiency is quieter than impossibility, that scientifically it can be more important. A process can fit the laws of physics and still strain the assumptions used in simulations. Gas cooling may be more effective in certain early halos. Star formation may ignite in brief, intense bursts. Dust may hide some galaxies and make others harder to classify. Black holes may regulate growth earlier than expected. Rare peaks in the density field may collapse faster than average regions. Observational selection may favor the brightest and most extreme systems. Each of these possibilities can reduce tension without breaking the larger model. But each also changes the story. If rare peaks explain the observations, then Webb may be finding the cosmic high mountains first, because high mountains are easiest to notice across deep time. If star formation was more efficient, then early galaxies may have converted gas into stars faster than many models expected. If masses are overestimated, then the tension weakens, but the measurement pipeline becomes the focus. If environments formed early, then galaxy evolution may have been shaped by cosmic geography sooner than we thought. No answer leaves the old picture untouched. This is the honest center of the documentary. The universe has not handed us a simple rebellion against physics. It has handed us a set of clues that make simple storytelling unsafe. The early universe was not merely a dark room where stars slowly appeared one by one. It was already a gravitational landscape. Some places were marked for faster growth. Some regions were destined to become crowded. Some paths were already guiding gas and galaxies toward future clusters. The old model was never that everything formed at the same pace everywhere. It already allowed unevenness. It already allowed rare events. It already knew that the densest regions would run ahead of the average universe. The tension comes from asking whether the most extreme early structures are only rare but expected, or whether their abundance, density, concentration, or maturity is telling us that some part of the model's small-scale physics needs revision. A human comparison helps, but only if we keep it limited. Imagine walking into a construction site at dawn and finding that most of the city is still only foundations, as expected. Then, on the horizon, a few towers are already standing. One tower might be explained by special planning, extra workers, or a head start. Several towers, in different places, force a different question. Did the construction schedule work differently than we thought? Webb is finding the distant towers, Some may turn out to be less massive than first estimated. Some may become clearer after spectroscopy. Some may fit simulations once selection effects and environment are included. But the reason astronomers keep returning to them is that they occupy the part of the map where timing matters most. They are not interesting because they are impossible. They are interesting because they are demanding. That demand reaches all the way down to dark matter. Cold dark matter is excellent at building structure because it can clump early and provide the gravitational wells ordinary matter later falls into. But different assumptions about dark matter behavior, matter density, fluctuation amplitude, feedback, and galaxy formation can change how quickly visible structures appear. The large-scale model may remain intact, while the small-scale recipes become more detailed. In modern cosmology, many tensions do not announce that the foundation is gone. They announce that the foundation is not the whole building. This is why Webb's evidence has such a specific emotional force. It does not give us the thrill of throwing away everything known. It gives us something more mature and more unsettling. The possibility that the universe is following the rules exactly, while our simplified version of those rules cannot keep up. The old model still stands because it explains too much to be casually abandoned. The new tension grows because Webb is showing details the old blur could not fully test. Between those two truths, the story becomes alive. We are not watching science collapse, we are watching its resolution increase. And as the resolution increases, the question shifts again. If the model allows rare early peaks, then the next step is to ask whether Webb is merely finding rare peaks, or whether those peaks belong to a deeper pattern of early structure that was already shaping galaxies before the universe looked ready. If those peaks belong to a deeper pattern, then Webb is not only finding early objects, it is finding early geography. That word matters. Geography means that location changes fate. On Earth, a river valley, a mountain pass, a coastline, or a desert can shape where people live, how they travel, what they build, and what they can become. In the universe, geography is stranger because it is mostly invisible. A galaxy's location inside the cosmic web can decide how much gas reaches it, how many neighbors disturb it, how quickly it grows, and when its star formation begins to fade. This is the midpoint shift. The structure is not a thing sitting beyond physics. It is the environment in which physics has been working all along. A young galaxy inside an early dense region is not merely a young galaxy with company, it is a galaxy inside a gravitational current. Matter is not arriving from all directions equally, it is flowing along filaments. Gas is being guided into halos. Neighboring galaxies are falling toward the same knots. The dark matter landscape gives some regions a head start, and that head start can echo through everything visible. This is why the word allowed becomes complicated. Physics allows the laws. It does not promise that our first simplified timeline will feel comfortable. The universe may allow rare, dense regions to collapse early because they were born from the highest peaks in the initial density field. It may allow galaxies there to grow rapidly because gas supply was concentrated. It may allow clusters to appear advanced because we are seeing the fastest places first. The real discomfort is not law-breaking. It is selection, timing, and amplification. A tiny early advantage can become enormous when gravity is given cosmic time. Imagine a nearly flat field after rain. Most of the water spreads thinly, but a slight depression collects a little more. Because it has more water, it deepens. Because it deepens, more water flows toward it. The original difference may be barely visible, but the feedback changes the landscape. Now replace water with matter, the field with expanding space, and the depression with a dark matter overdensity. That is the beginning of cosmic structure. The early universe did not need to draw the full web at once. It only needed to provide the seeds that gravity could not forget. That is why the cosmic microwave background is so important to this story, even though Webb does not observe it directly. The microwave background shows the universe when it was about 380,000 years old, long before galaxies filled the dark. It shows tiny temperature variations, faint density differences that later grew into the web. Those variations are not the web itself. They are more like the first fingerprints of the process that would eventually become filaments, clusters, and voids. Webb enters billions of years later in the story, but still early enough to test how fast those fingerprints became architecture. When it sees galaxies in dense environments, it is looking at the visible response to invisible beginnings. A crowded early region may be the grown version of a high-density patch from the young universe. A filament may be the path along which matter kept falling. A protocluster may be a knot still assembling, not yet a modern cluster, but already dense enough to shape the galaxies inside it. This makes the title more subtle and more powerful. A structure bigger than physics should allow is not really about one forbidden size. It is about whether the chain from tiny fluctuation to visible architecture unfolded faster, cleaner, or more efficiently than expected. And the word expected carries a lot of weight. Expectations come from simulations, statistical models, previous surveys, and physical assumptions about dark matter, gas, star formation, feedback, and expansion. A simulation can grow a universe from early conditions and ask what kinds of structures should appear at different times. But simulations must make choices. They cannot track every atom in the visible universe. They approximate gas cooling, star formation, stellar explosions, black hole feedback, dust, radiation, and many other processes. Some parts are grounded. Others are modeled through recipes because the physics is too complex to compute directly at every scale. So when Webb finds a dense early region, the tension may come from the universe, or from the recipes, or from the measurement, or from all three. That is not a weakness in science, it is the way science becomes sharper. The observation presses against the model. The model says what should be common, rare, or nearly absent. The telescope finds what is actually there. If the two disagree, researchers do not have to choose immediately between triumph and collapse. They ask where the disagreement lives. Does it live in the redshift estimate? In the mass estimate? In the assumed star formation history? In the dark matter halo growth? In the survey volume? In the statistics of rare objects? In the baryonic physics that turns gas into visible galaxies? Each location has a different consequence. This is why the middle of the story cannot simply get louder. The real drama is diagnostic. A structure that appears too mature may be telling us that early galaxies formed stars more intensely than expected, or that dust makes some systems look older or heavier, or that dense regions lit up quickly because gas streams from filaments fed them efficiently, or that the most extreme peaks of dark matter collapse are more visible to Webb than average regions, or that some assumptions in the growth of structure may need to be tested against a larger sample. The next step is not to declare the universe impossible. The next step is to follow the pressure into the environment itself. In a dense cosmic node, gravity changes the rules of ordinary galaxy life. Galaxies do not evolve in isolation. They fall, merge, strip, feed, heat, and disturb one another. Gas flows along filaments like fuel entering a furnace. Starbursts can ignite and then exhaust themselves. Black holes can grow in the centers of galaxies and push energy back outward. The same environment that helps galaxies grow can later begin to shut them down. That double role is crucial. A dense region is both nursery and trap. Early on, density can accelerate formation. More matter is available. More interactions occur. More gas flows inward. Later, the same density can heat gas, strip fuel, and reduce star formation. In the nearby universe, rich clusters often contain many old, red, quiet galaxies. But in the early universe, the balance may still be changing. Webb can catch dense environments while they are still being built, while the machinery of growth has not yet fully turned into the machinery of shutdown. That is a more interesting story than a giant object violating a rule. It is a story about timing. When does environment begin to matter? When does a filament become a supply line? When does a knot become a cluster? When does a crowded region stop feeding galaxies and start starving them? The universe's largest structures are not large only because they stretch across space. They are large because they control histories. A galaxy born inside a dense early node carries the consequences of that location for billions of years. Its stars, its gas, its mergers, its black hole, its final color and shape may all be influenced by a density difference that began before the first light. That means the cosmic web is not background. It is ancestry. And if Webb is now revealing that ancestry closer to its beginning, then the pressure moves from object to origin. The question is not simply how big the structure became. The question is how early the universe began assigning galaxies to different futures. That is the moment the story changes shape. The structure was not built like a wall. It grew like a memory. A wall is assembled from separate pieces, brick after brick, stone after stone, layer after layer. The shape appears because something outside it decides where each piece should go. That is not how the cosmic web formed. No hand placed galaxies along filaments. No force drew bright lines through empty space in one sudden act. The web grew because the universe began with differences it could never fully erase. A slightly denser region was not only denser for an instant, it became a place where gravity had a little more authority. That authority attracted more matter. More matter deepened the gravity. Deeper gravity attracted still more. Over time, the original difference stopped looking small. It became a path, then a filament, then a node, then, perhaps, a future cluster. The universe remembered the imbalance by making it larger. This is why James Webb's deepest images are not simply looking backward. They are watching memory become visible. When Webb reveals a dense region in the early universe, it is not showing a random crowd of galaxies that happen to gather. It may be showing a place where the initial conditions of the universe had already begun to express themselves. The galaxies are bright, but the cause is older than the galaxies. The stars are new, but the gravitational preference is ancient. Long before those stars formed, before heavy elements spread through space, before planets could exist, the matter in that region already had a slightly different future. It means that the largest structures in the universe are not only built across space, they are built across cores. A filament is not just a long arrangement of galaxies. It is a history of matter responding again and again to the same hidden gradient. A void is not merely emptiness. It is the region left behind as matter moved toward denser places. A cluster is not merely a crowded city of galaxies. It is the endpoint of an advantage that began almost invisibly. This is also why the early web can feel as if it is larger than physics should allow. Human minds are poor at exponential growth, and gravity is one of the great amplifiers in nature. We notice the final size and forget the slow multiplication. We see the distant knot and imagine it had to be assembled from nothing. But it was not assembled from nothing. It was amplified from a difference. The difficult question is whether the amplification was as fast as expected. In the standard picture, dark matter carries most of the early burden. It forms halos and filaments before ordinary matter can fully cool and shine. Gas then falls into these wells, heats as it collapses, cools where conditions allow, and forms the first generations of stars. Star formation changes the gas by producing radiation, winds, supernovae, and heavier elements. Black holes may grow in the centers of young galaxies, feeding on gas and releasing energy back into their surroundings. Every stage changes the next. That chain is not simple. Gravity competes with pressure, cooling, turbulence, radiation, feedback, mergers, and expansion. A region can have enough dark matter to attract gas, but if the gas remains too hot, stars may form slowly. A galaxy can form stars rapidly, but strong feedback can drive gas out. A cluster can gather galaxies, but its hot environment can later starve them. Structure is not a single process. It is a negotiation between processes. So when Webb finds signs of early dense environments, the question becomes more precise than the title first suggests. Did dark matter collapse earlier in rare peaks? Did gas cool more efficiently inside those peaks? Did star formation proceed in bursts that made young galaxies appear massive quickly? Did mergers accelerate growth? Did dust and modeling make some galaxies look older or heavier than they are? Did earlier surveys miss the faint members that reveal how common these environments really are? Each answer changes where the pressure lands. If the issue is dark matter assembly, then cosmologists may need to examine the statistics of the highest peaks. If the issue is gas physics, then galaxy formation models need sharper recipes for cooling, turbulence, and feedback. If the issue is star formation efficiency, then the early universe may have turned gas into stars more aggressively in certain environments. If the issue is measurement, then spectroscopy and deeper surveys will narrow the uncertainty. None of these routes is boring. Each makes the universe more exact. And exactness is the real opposite of hype. A fake mystery grows by becoming vague. A real scientific mystery grows by becoming narrower. It starts as a dramatic question. Did Webb find something too big? Then it becomes a better question. How rapidly can dark matter, gas, and galaxies assemble in the densest early regions? Then it becomes sharper still. Which part of the chain is responsible for the apparent speed? The midpoint is not where the video should repeat the opening. It is where the viewer realizes that the giant structure is not the real monster. The real monster is the efficiency of gravity when given even the smallest head start. The surprise is that the structure may have begun declaring itself before the universe looked old enough to have such a memory. There is a strange emotional weight in that. We like to imagine the early universe as simple, hot, smooth, young, unfinished. But simple does not mean featureless. Smooth does not mean identical. Young does not mean blank. The young universe already contained the faint instructions for later complexity. Galaxies did not appear on an empty page. They appeared on a page where the pressure marks were already present, invisible until light began to reveal them. James Webb is reading those pressure marks. It reads them through red-shifted light, through faint infrared colors, through galaxies too small or distant for older instruments to place clearly, through the density of sources across a field, through arcs of lensed background light, through the relationship between bright galaxies and their fainter companions. It reads them imperfectly, but more deeply than before. And every improvement makes the early map less blank. That is why the most important image is not a single galaxy. It is the arrangement. A single ancient galaxy can be spectacular because it tells us that stars were forming early. But an arrangement tells us that stars were forming inside an environment. It says the galaxy had neighbors, direction, density, and a place in the web. It says the universe was not only making lights, it was making neighborhoods, and neighborhoods become destiny. A galaxy in a dense node may grow quickly, merge often, and exhaust its gas early. A galaxy in a filament may be fed for longer. A galaxy in a quieter region may evolve more slowly. Over billions of years, these different environments help create the variety of galaxies we see today. Spirals rich in gas, ellipticals filled with old stars, clusters crowded with quiet galaxies, void galaxies living in relative isolation. The cosmic web is therefore not only ancient structure, it is the beginning of difference. Once that is understood, the title becomes less like an accusation against physics and more like an invitation to measure its patience. The universe may not have broken a law. It may have obeyed the law so effectively that our simplified expectations fell behind. And if early structure is memory made visible, then the next question is unavoidable. What happens to the galaxies born inside that memory? Do they simply trace the web? Or does the web begin to change them from the moment they appear? A galaxy does not grow alone just because space around it looks empty. Even a lonely-looking galaxy is moving through a larger gravitational landscape. It may sit inside a dark matter halo, near a filament, beside a forming group, or at the edge of a region where matter is slowly draining toward a denser knot. Its future depends not only on how much gas it contains, but on where the universe placed it. This is the consequence of the midpoint. If the cosmic web is memory made visible, then galaxies are not merely lights along the memory, they are shaped by it. In the simplest picture, a galaxy grows by pulling in gas, turning some of that gas into stars and changing over time as stars age, explode, and enrich the surrounding material with heavier elements. That picture is useful, but incomplete. Gas does not arrive from nowhere. It follows gravity. It moves along filaments. It falls into dark matter halos. It can be heated, compressed, stripped, stirred, or denied. The surrounding environment decides whether the galaxy has fuel, pressure, neighbors, and time. That is why dense early structure matters so much. It may be the place where galaxy evolution accelerates. Inside a dense region, a young galaxy can receive gas more efficiently because more matter is already flowing toward the same gravitational basin. It can encounter other galaxies more often, and those encounters can drive gas inward, triggering bursts of star formation. Its central black hole may grow faster because gas is being disturbed and funneled toward the core. The same processes that make the galaxy bright enough for Webb to detect can also make it evolve quickly enough to become surprising. This creates a strange double image. To Webb, the galaxy may appear as a faint infrared smudge, only a few pixels of ancient light. But physically, that smudge may represent billions of stars forming in a crowded young environment. Gas clouds collapsing, supernovae injecting energy, dust forming from heavy elements, and gravity pulling more material along invisible roads. The image is quiet because the universe is distant. The process behind it is violent in slow motion. The environment also changes what scientists expect to find. A galaxy in an average region may grow more gradually. A galaxy in a rare, overdense region may grow faster, merge sooner, and become massive earlier. If Webb surveys preferentially reveal bright galaxies in these dense places, then the early universe may look more mature than the average universe truly was. That does not make the observations wrong. It means the observations are biased toward the places where growth was easiest to see. Selection is not a flaw. It is a condition of looking. When you look across billions of light years, you do not see every galaxy equally. You see the ones bright enough, large enough, active enough, or exposed enough for the telescope and filters to catch. Faint companions may be missed. Dusty galaxies may hide. Quieter systems may sink below detection thresholds. A survey can therefore reveal real structure while still leaving part of the population invisible. The map is powerful, but it is not complete. That incompleteness matters when the title speaks of something too large. A structure may seem sharper once its brightest members are identified, then change shape when fainter galaxies are added. A dense region may become more convincing with better redshifts, or less dramatic if some apparent members move to different distances. A massive galaxy may become less massive after improved modelling, or more interesting if spectroscopy confirms it. Every new measurement either tightens the pressure or moves it somewhere more precise. This is how the real story advances, not by repeating that the structure is enormous, but by asking what the environment does. One of the most important environmental effects is accelerated star formation. In the early universe, gas was abundant, galaxies were smaller, and merger rates were higher. Dense regions could push these factors further. Gas-rich galaxies falling together can compress their gas. Compressed gas forms stars. Those stars produce ultraviolet light, winds, and supernovae. They enrich the gas with carbon, oxygen, silicon, iron, and dust. Suddenly, a young galaxy begins to carry chemical signs of age. That can fool intuition. A galaxy can be young by cosmic time and already chemically busy. It can exist less than a few billion years after the Big Bang and still contain multiple generations of stars. It can look mature, not because it is impossibly old, but because it lived fast in a dense environment. But fast living has consequences. Star formation consumes gas. Supernovae heat and disturb it. Black holes can inject energy through jets or radiation. Nearby galaxies can pull gas away or drive it inward. In a forming cluster, hot gas between galaxies can begin to resist further cooling. Over time, the same dense environment that helped galaxies grow can begin to restrict them. It can turn a nursery into a trap. This is one of the deepest reasons early structure matters. It tells us when the universe began creating not only galaxies, but different kinds of galaxies: blue, star-forming systems; red, quiet systems; gas-rich disks; compact spheroids; cluster galaxies shaped by crowding; field galaxies shaped by relative isolation. If environment began influencing these differences earlier than expected, then the Webb was not a late background. It was an early author. A human mind tends to see a galaxy as an individual, a beautiful spiral, an elliptical glow, a distant red dot. But a galaxy is also a biography of place. Its shape records mergers. Its color records star formation. Its gas records supply and loss. Its black hole records feeding history. Its surroundings record whether gravity gave it neighbors or left it alone. To understand the galaxy, you have to understand the web around it. That is why Webb's early maps are so valuable. They do not only ask how many galaxies existed, they ask where galaxies existed relative to one another. They ask whether the first bright systems were isolated sparks or members of larger environments. They ask whether early cosmic structure was already sorting galaxies into different evolutionary paths. The answer is not finished. It is being built field by field, spectrum by spectrum, redshift by redshift. But the direction is clear enough to change the emotional meaning of the title. The structure is not frightening because it is a monster outside physics. It is unsettling because it suggests that the universe's largest architecture may have started shaping small galaxies before those galaxies had time to look settle. And once environment begins acting that early, the next pressure becomes harder to avoid. If galaxies are being shaped by the web, then the web itself must already be coherent enough to matter. If the web is coherent enough to matter, then the next question is not whether the structure exists, but what kind of explanation can survive it. There is never only one explanation at the edge of a measurement. That is why careful science moves more slowly than a headline. A dramatic title can point to the pressure in one sentence, but the pressure itself has to be sorted. Is the structure truly as large as it appears? Are the galaxies really at the same cosmic distance? Is the mass estimate stable? Is the sample unusual because Webb is excellent at finding the brightest early systems? Or is the early universe genuinely building dense environments faster than many models expected? Each possibility keeps a different door open. The simplest door is measurement refinement. Deep cosmic maps are not made from perfect distances. Photometric redshifts are powerful, but they are not final. They estimate distance from colours, and colours can be affected by dust, age, metallicity, emission lines, and the limits of the filters. A galaxy may look farther away than it is if its light mimics the signature of cosmic expansion. Another may look more massive if its star formation history is modelled incorrectly. A dense region may gain or lose members as better data arrives. This does not make early structure disappear. It means the first version of the map is not the last version. The stronger door is spectroscopy. When astronomers obtain spectra, they can identify specific features in the light and pin redshift more precisely. A spectral line shifted into the infrared can turn a probable distance into a much firmer one. A group of galaxies with confirmed redshifts becomes far harder to dismiss as projection. If the redshifts hold, the structure becomes more real. If some redshifts move, the structure changes shape. That is why Webb's discoveries often begin as pressure and then wait for confirmation. The telescope can reveal candidates quickly, but certainty grows through follow-up. The public sees the first dramatic version. Science lives through the slower second and third versions, where the object is remeasured, modelled, challenged, and either weakened or strengthened. Another door is selection effect. Webb is not a random pair of eyes wandering through the universe. It is an extraordinarily sensitive instrument, often pointed at fields chosen for scientific value. Deep surveys are designed to find faint, ancient galaxies. But the galaxies easiest to detect at great distances may be the ones forming stars rapidly, shining brightly, or living in regions where growth is accelerated. The early universe we detect first may not be average. It may be the bright edge of the distribution. This is not deception. It is astronomy. If you stand on a shore at night, the first ships you see are the ones with the brightest lights. That does not mean every ship is bright, and it does not mean the ocean is empty between them. It means your first map is biased toward what announces itself. Webb's first deep maps may work the same way. The most luminous galaxies, densest regions, and strongest lensing systems step forward first because the universe has made them visible across immense distance. Then there is the rare peak explanation. In lambda CDM, the early universe is not uniform in every patch. Some regions begin slightly denser than average. Most grow slowly. A few grow quickly. The highest peaks in the density field can collapse earlier, gather more mass, and become the ancestors of rich clusters. If Webb finds one of these rare peaks, the structure may look surprising because it is rare, not because it is forbidden. Rare does not mean impossible, but rare does mean we must count carefully. If a survey volume is large enough, it should find some extreme regions. If the number of extreme regions matches predictions, the model survives comfortably. If the number is too high, the pressure increases. If their masses or concentrations are systematically too large, the pressure shifts again. The key is not the existence of one stunning example. The key is the population. This is where statistics enters quietly behind the cinematic image. A single early cluster may become famous. A single filament may become a headline. But cosmology cares about abundance. How many systems of this mass should exist at this redshift? How many overdense regions should appear in a survey of this size? How strongly should environment affect galaxy properties at that cosmic time? The answers are not judged by awe. They are judged against distributions. There is also the possibility that the galaxy physics is doing more work than expected. Dark matter may provide the scaffolding, but visible galaxies depend on ordinary matter, and ordinary matter is messy. Gas cools, fragments, forms stars, absorbs radiation, becomes dusty, is blown outward by supernovae, and is stirred by black holes. Small changes in these processes can alter how bright, massive, or mature early galaxies appear. If star formation was burstier in early dense regions, a young galaxy could look temporarily overgrown. If dust hides part of the light, the galaxy may be misread. If feedback is weaker or delayed, gas may turn into stars more efficiently. This explanation preserves the broad cosmology but changes the small-scale story. The skeleton may be familiar, but the lamps along it may burn differently than expected. A more daring door is new physics, but it should be opened last, not first. New physics may involve dark matter properties, early dark energy, primordial fluctuations, or changes in how structure grows. But responsible science does not jump there because a title sounds exciting. It first exhausts measurement uncertainty, selection effects, rare peaks, astrophysical recipes, and simulation limits. Only when ordinary explanations fail repeatedly does the deeper model become the target. That restraint does not make the story smaller. It makes it trustworthy. The strongest mysteries are the ones that survive the boring explanations. If better redshifts confirm the members, if mass estimates remain high, if larger surveys find more examples than expected, if simulations cannot reproduce the population without changing assumptions, then the pressure becomes more serious. Not because anyone shouted that physics is broken, but because the safe exits became narrower. This is the real drama of Webb's structure. It stands at a crossroads where several explanations remain alive. Measurement may soften it. Selection may explain part of it. Rare density peaks may explain another part. Galaxy physics may accelerate the visible growth. Model refinements may close the gap. Or, if the gap survives, the structure may become one more reason cosmologists ask whether the early universe carried something we have not yet described correctly. At this stage, the honest ending of every explanation is a boundary, not a verdict. We know the universe has a web. We know galaxies trace it imperfectly. We know dark matter must be part of the scaffolding. We know Webb is pushing the map deeper into time. What remains unsettled is how quickly the densest parts of that web became capable of shaping galaxies, bending light, and looking mature. And that unsettled boundary is exactly where the next layer begins, because every explanation depends on the same fragile bridge, the limits of the instruments that carry ancient light into human understanding. Every explanation now depends on a fragile act of translation. The universe does not send us objects, it sends us light. That light has crossed expanding space, passed through dust, blended with the glow of stars, lost energy into redshift, and arrived as a small electrical signal inside a detector colder than almost anything on Earth. Between the ancient structure and the human mind stands an instrument, a model, and a chain of assumptions. This does not weaken Webb's discoveries. It makes them more remarkable. A human eye could never see what Webb sees. If you stood under the darkest sky on Earth, the galaxies that matter most to this story would still be beyond you. Their light is too faint, too stretched, too ancient. Your eyes evolved for sunlight, firelight, faces, movement, and danger nearby. They were not built to catch infrared photons from galaxies whose light began travelling before the Milky Way looked the way it does today. Webb is, in that sense, an extension of human senses into deep time. Its mirror gathers light that no eye could hold. Its instruments separate that light into colours and sometimes spectra. Its detectors turn photons into data. But the telescope does not understand the data. People do. And people must ask what part of the signal comes from distance, what part comes from dust, what part comes from age, what part comes from star formation, and what part comes from the limits of the observation. That is why the boundary between discovery and interpretation is so important. When Webb observes an early galaxy, astronomers may estimate its redshift from photometry, using brightness across several filters. This gives a probable distance and age, but not always a final one. Spectroscopy can sharpen the result by identifying specific lines or breaks in the light, but spectroscopy is expensive in telescope time and difficult for the faintest objects. The deepest structures are often the hardest to confirm in full. So the map begins with probability. A galaxy may have a most likely redshift. A cluster candidate may have likely members. A dense region may have statistical significance. A lensed arc may be modelled through a mass distribution that fits the distortion. None of this is casual. It is not guessing. But it is also not the same as holding the object in a laboratory. Astronomy lives with distance as a permanent condition. That distance changes the emotional meaning of certainty. On Earth, certainty often feels like touch. You can weigh a stone, cut into a tree, drill ice, collect a sample, repeat an experiment. In deep cosmology, certainty is built differently. It comes from consistency across signals. Colours agree with redshifts. Redshifts agree with positions. Positions agree with density. Density agrees with lensing. Lensing agrees with mass. The structure becomes deliberate when different kinds of evidence lean in the same direction. This is why a single measurement is rarely enough. A photometric overdensity suggests a region. Spectroscopic confirmation strengthens it. Lensing reveals hidden mass. Galaxy colours reveal age and star formation history. Infrared brightness reveals old stars or dust-obscured activity. X-ray observations, when available, can reveal hot gas in clusters. Radio or millimeter observations can trace cold gas and dust. Each instrument sees a different version of the same reality, and the strongest story is the one that survives when those versions are compared. Webb is powerful, But it is not alone. Its deepest value often comes when its infrared vision is combined with older surveys, ground-based telescopes, Hubble imaging, sub-millimeter observatories, X-ray telescopes, and simulations. A structure that first appears as faint infrared points can become more physical when other wavelengths show gas, dust, lensing, or star formation. The universe is too complicated for one eye, even one as extraordinary as Webb. And yet every added instrument brings its own limits. A survey has a footprint, the area of sky it covers. A deep survey may see faint galaxies but only across a narrow field. A wide survey may cover more sky but miss the faintest members. A filter set may be excellent for some redshifts and less clean for others. A lensing model may depend on identifying background sources correctly. A mass estimate may change when the assumed stellar population changes. The shape of the final structure can shift as the evidence improves. This is not failure. It is refinement. Think again of the dark valley with lamps on distant hills. The first lamps suggest a road. More lamps reveal a bend. A height map reveals the valley floor. A weather map shows where fog hid smaller lights. A better distance estimate moves one lamp from the road to a different hill. The map changes, but the valley does not vanish. The change means you are learning which parts were real, which parts were guessed, and which parts were waiting for better sight. The early universe has to be mapped with that kind of patience. The danger of a title like this is that it can make the viewer imagine a single clean answer. Webb found a structure, the structure is too big, physics failed. But real instruments produce something more interesting. They produce pressure gradients of confidence. Some parts of the story affirm the cosmic web exists, dark matter shapes it, galaxies trace it. Webb sees early galaxies in infrared. Dense environments can be identified statistically. Massive structures can bend light. Other parts are still being narrowed. Exact masses, exact memberships, exact abundance, exact formation history. That layered certainty is not a weakness in the narration. It is the truth that makes the narration worth trusting. A tired listener does not need fake certainty to stay. Often the opposite is more powerful. There is a calm intensity in hearing where the boundary lies. This is known. This is inferred. This is modelled. This is still being tested. The universe becomes larger, not because we pretend to know everything, but because we can see exactly where knowledge ends. And Webb has moved that ending line. Before Webb, the earliest galaxies and environments were often blurred by distance, limited sensitivity, and missing infrared detail. Webb does not remove all uncertainty, but it pushes uncertainty into a smaller space. Faint galaxies become measurable. Redder light becomes accessible. Cluster members become clearer. Lensed arcs become sharper. The first maps of early dense regions become less like rumours and more like evidence. That is why the structure feels so unsettling. It is not born from a wild claim. It is born from improved sight. The better the instrument becomes, the less the early universe resembles a blank beginning. The more carefully the light is sorted, the more the darkness fills with relationships. Still, every map carries one final human limit. We are trying to understand a structure too large to experience, too old to witness directly, and too distant to touch. Using light that left before Earth had oceans in their present form. We are asking detectors, equations, and models to do what no body can do. Stand inside cosmic history and look around. And because the instrument has carried us this far, the next pressure is not only scientific, it is historical. Every time humanity has built a better cosmic map, the universe has turned out to be less centered on us, less simple than we hoped, and more structured than the previous generation could see. Every better map of the universe has taken something that once looked simple and made it stranger. At first, the sky seemed like a dome of lights. The stars appeared fixed, scattered across darkness in patterns that human cultures turned into animals, heroes, gods, warnings, calendars, and stories. That was not ignorance. It was the only map the naked eye could make. The universe available to human senses was beautiful, but shallow. It had no depth except imagination. Then telescopes gave the stars distance, multiplicity, and hidden structure. Some lights became planets, some fuzzy patches became nebulae, some nebulae became galaxies. The Milky Way stopped being the whole island of creation and became one galaxy among many. The universe did not change. The map did. Later, redshift gave the map a third dimension and a history. Galaxies were not only located on the sky, their light carried evidence of recession, expansion, and distance. A galaxy was not merely over there, it was also back then. Space became time made visible. The farther astronomers looked, the younger the universe became. That historical depth changed everything. Once galaxies could be placed in 3 dimensions, they stopped looking randomly scattered. Surveys began revealing walls, filaments, clusters, and voids. What had seemed like an even distribution became a network. The universe was not centered on us, but it was also not featureless. It had architecture on scales no ancient observer could have imagined. Each step followed the same pattern. Better instruments did not make the universe less mysterious by explaining it away. They made the mystery more exact. The Milky Way became one galaxy. Galaxies became traces of expansion. Redshift maps became evidence of the cosmic web. The cosmic microwave background became a photograph of early unevenness. Dark matter became the invisible mass needed to explain the structure gravity had built. James Webb belongs to that same history, but with a different kind of pressure. It is not merely expanding the map outward, it is pushing the map backward, toward the period when galaxies and environments were still taking shape. It is asking whether the cosmic web was already leaving visible fingerprints earlier than expected. It is taking the structure that nearby surveys made familiar and moving it into an age where every object has less time behind it. That is why the title feels modern. A century ago, the shock was that galaxies existed beyond the Milky Way. Later, the shock was that the universe was expanding. Later still, the shock was that ordinary matter was not enough to explain galactic motion and cluster mass. Now the shock is subtler. The broad cosmic model is strong, but the first chapters are becoming crowded with detail. The early universe is no longer a blank preface. It contains galaxies brighter than expected, massive candidates that demand careful modelling, black holes whose growth histories are being tested, dust where dust must have formed quickly, and dense regions that hint at early environment. Not all early claims survive unchanged. Some weaken after better data, some shift when redshifts improve, some become less dramatic but more precise. That is not a retreat. That is how the first map becomes a real one. The historical lesson is that astronomy advances by replacing clean myths with complicated truth. One myth is that the universe should look random unless something dramatic forced it into order. Another myth is that the early universe should look simple because it was young. But youth in cosmology is not the same as emptiness. A child can carry inherited features before it has lived long. The early universe carried inherited density differences before the first galaxies had fully grown. Webb is not finding order from nowhere. It is finding the visible consequences of an older pattern. There is another historical lesson, too. Every time the map improves, humanity loses a comforting scale. The Earth was not the center. The Sun was not unique. The Milky Way was not the universe. Visible matter was not most of the matter. Now even the idea of a slow, easily pictured cosmic dawn is under pressure. The first billion years may have been more active, more varied, and more environmentally structured than the simple version suggested. This does not mean every surprising object is revolutionary. Many will become ordinary once enough context exists. In science, today's anomaly can become tomorrow's calibration point. A structure that seems shocking in a small sample may become expected in a larger one. A mass that appears too high may settle downward. A redshift may be refined. A model may improve. But sometimes, after all those corrections, something remains. That remainder is where history moves. The cosmic web itself was once a remainder. If galaxies had been evenly distributed, the story would have been simpler. But surveys kept finding structure. The pattern survived more data. It became too large and too consistent to ignore. Eventually, the web stopped being an oddity and became the expected outcome of gravitational growth in a dark matter-dominated universe. What once looked strange became evidence that the model was working. Webb may repeat that pattern at earlier times. Some early structures may become less shocking as models improve. Others may become anchor points showing how the densest regions formed first. Some may reveal that galaxy formation inside rare peaks was more efficient. Some may force better simulations of gas, feedback, and environment. A few may remain uncomfortable enough to push deeper questions about dark matter, initial fluctuations, or cosmic expansion. The historical stakes are therefore not that one telescope image will overthrow physics. The stakes are that a new generation of maps may decide which parts of our story are robust, which parts are approximate, and which parts were only comfortable because we could not yet see enough. That is a quieter kind of revolution. No trumpet sounds when a redshift is confirmed. No law shatters when a lensing model improves. No one sees dark matter directly when a cluster arc is fitted. Yet each small correction changes the map. A galaxy moves from candidate to confirmed. A dense region becomes a protocluster. A projected pattern becomes a physical association. A suspected mass becomes a gravitational measurement. Slowly, the universe becomes less vague. And as it becomes less vague, it becomes harder to hide behind simple phrases. Too big is not enough. Too big compared with what? At what redshift? In what survey volume? With what mass estimate? Confirmed by which method? How many similar structures exist? How does the abundance compare with simulations? What assumptions control the result? These questions do not weaken the wonder. They turn wonder into something strong enough to survive scrutiny. That is the gift of historical perspective. It reminds us that every great cosmic surprise must pass through measurement before it becomes knowledge. Webb has brought us to one of those thresholds. The darkness is filling with early relationships. The web is no longer only the mature structure of a late universe. It may be visible closer to the time when its first bright traces appeared. And, if that is true, then the next stage is not to ask whether physics failed, but to gather the mechanisms that could make such early order possible. The mechanisms do not point in one direction by accident. Dark matter, gas, gravity, feedback, mergers, radiation, dust, and time all seem like separate ingredients when we name them one by one. But inside the early universe, they were not separate chapters. They were acting on each other constantly, A dark matter halo changed where gas could fall. Gas cooling changed where stars could form. Stars changed the gas by heating it, enriching it, and sometimes throwing it outward. Black holes changed the centers of galaxies. Filaments changed the supply lines. Mergers changed the shapes, masses and internal motions of galaxies. The web changed the environment, and the environment changed the galaxies that traced the web. This is why a structure can feel too large before it is truly forbidden. The eye sees a big pattern. The model sees many processes that had to coordinate within limited time. The pressure does not come from a single number floating in space. It comes from the whole chain needing to work efficiently enough that an early dense region becomes visible, massive, and organized before intuition is ready for it. Start with dark matter. Without it, the web would be hard to build. Ordinary matter alone would have been too tied to radiation in the early universe, too pressured, too delayed. Dark matter gave gravity a head start. It made invisible wells before stars existed. Those wells did not shine, but they created preference. They told later gas where to collect. In that sense, the first architecture of the universe was dark. Then gas entered the story. Gas does not become stars simply because gravity wants it to. It has to cool. It has to lose energy. It has to become dense enough for parts of it to collapse. If it remains hot and supported by pressure, it resists star formation. If it cools efficiently, it fragments. In the first galaxies, cooling depended on conditions very different from those inside the modern Milky Way. The gas had fewer heavy elements at first, because heavy elements had to be made by stars. Early cooling channels, radiation fields, and chemical enrichment all mattered. Once stars formed, they changed everything around them. Massive stars lived fast and died violently. They released ultraviolet light, powerful winds, and supernova explosions. They produced heavy elements and dust, changing future gas clouds so that later star formation could proceed differently. In a young galaxy, one intense burst of star formation could make the system visible across enormous distance, but it could also disturb the fuel needed for the next burst. Growth was never smooth. It was pulsed, unstable, and shaped by feedback. Feedback is one of the most important words in this story because it prevents simple thinking. Without feedback, gas could fall into halos and turn into stars too easily. Galaxies in simulations would often become too massive too quickly. With feedback, star formation can regulate itself. Supernovae heat gas, stellar winds push material outward, radiation changes the surrounding medium, black holes can inject energy on larger scales. The same processes that build a bright galaxy also limit its growth. So when Webb sees early galaxies that appear massive or mature, scientists are not only asking how gravity assembled them, they are asking how feedback allowed or restricted them. Was feedback weaker in some early environments? Was gas supply so strong along filaments that it overcame outflows? Did galaxies grow in short, bright bursts that make them appear unusually advanced? Did dense regions recycle gas more efficiently? Each possibility changes the meaning of the structure. Then come mergers. In a crowded environment, galaxies meet more often. They may not collide like solid objects, because the distances between stars are still enormous. But their gravity can distort one another. Gas can be driven inward, starbursts can ignite, central black holes can be fed, smaller galaxies can be absorbed into larger ones. Over time, mergers help build mass and transform shape. In early dense regions, frequent interactions could accelerate growth. that mergers also require time. That is why the early universe is such a harsh test. A present-day cluster can look mature because billions of years of mergers and infall have shaped it. A high redshift cluster, or protocluster, has had less time. If it already contains massive galaxies, strong density contrast, or lensing mass, then the merger history, gas history, and dark matter history all have to be compressed into a shorter interval. The filaments make that compression possible, but also more complicated. A filament is not just a line on a map. It is a preferred path for matter. Gas and galaxies can flow along it toward denser nodes. A node at the intersection of several filaments can receive fuel from multiple directions. This may help explain why some regions grow faster than average. They are not isolated containers. They are fed systems. The image is calm from far away. Dots on blackness, faint red smudges, quiet arcs of light. But underneath that calm is transport. Matter is moving, gas is heating and cooling, galaxies are falling into shared gravitational wells, dark matter is merging invisibly. The structure is alive in the only way cosmic structure can be alive, not biologically, but dynamically, through motion across time. That is why the web is more than a background. It is the stage, the supply chain, the pressure field, and the record of growth. A galaxy inside a filament does not experience the same history as one inside a void. A galaxy near a node does not evolve like one far from dense structure. A cluster core does not simply contain galaxies, it changes them. Environment is not scenery. Environment is physics with geography. The question Webb sharpens is how early that geography became active. If environmental effects appear early, then the web was already coherent enough to influence growth. If dense regions already contain mature-looking galaxies, then gas supply and star formation may have been accelerated there. If lensing reveals concentrated mass, then dark matter had already gathered strongly. If surveys show large-scale patterns at high redshift, then the cosmic map was not waiting until late times to become organized. The mechanisms therefore converge on one idea. Structure is not a late decoration added after galaxies formed. It may be part of the reason galaxies became what they are. That changes the emotional frame of the title. The unsettling thing is not that Webb found one giant object sitting in defiance of physics. The unsettling thing is that Webb may be showing us the universe's growth machinery while it is still young, already coordinated across scales that human life cannot feel. Tiny early fluctuations, invisible dark matter wells, gas streams, star formation, mergers, and feedback all combine until the final pattern looks almost intentional. But it is not intentional. It is lawful. That may be the deeper unease. A random universe would be easier to dismiss. A broken universe would be easier to dramatize. But a lawful universe that builds vast structure from almost invisible beginnings is harder to absorb. It means the web did not need a miracle. It needed a slight imbalance. Gravity, dark matter, and time. The remaining uncertainty is how much time was enough. If Webb's early structures continue to hold under better measurements, then the mechanisms will have to be tuned more carefully. The dark matter story, the gas story, the star formation story, the feedback story, and the environmental story must all fit together without cheating the clock. The laws may remain intact, but the details will have less room to be vague. And that brings us to the final boundary of knowledge. We can now see enough to know that the early universe was not blank. We can see enough to know that structure was forming. We can see enough to feel the pressure. but we still have to decide exactly where the pressure belongs. The pressure belongs in the boundary between what is already known and what is still becoming measurable. That boundary is not a clean wall, it is a moving line. On one side, the universe has given us evidence strong enough to stand on. On the other side, there are interpretations that remain open, competing, or incomplete. Webb has pushed the line farther into the early universe, but it has not erased the need for caution. In fact, the farther it reaches, the more valuable caution becomes. We know the universe is structured. That is no longer in doubt. Galaxies do not fill space evenly. They gather along filaments, avoid voids, and cluster at nodes where gravity has concentrated matter. The cosmic web is a real feature of the universe, not an illusion made by imagination. It appears in redshift surveys, simulations, gravitational lensing, cluster distributions, and the way galaxies relate to their environments. Any final explanation has to begin there. We know dark matter is central to that structure. The visible galaxies are not enough to explain the architecture by themselves. Their stars and gas do not provide the necessary gravitational scaffolding. Dark matter halos, filaments, and larger mass concentrations guide where ordinary matter falls and where galaxies form. Webb does not directly see dark matter, but it sees the galaxies and lensing effects that reveal where dark matter has shaped the scene. The structure is luminous at the surface and dark at the root. We know the early universe was not blank. The cosmic microwave background already told us that the young universe contained tiny variations. Webb now helps us see the later consequences of those variations as the first visible generations of galaxies and environments emerge. The surprise is not that structure exists. The surprise is how quickly some structures seem to become visible, dense, or influential. That is the known side. The uncertain side begins with exact timing. How early did the densest environments become coherent enough to shape galaxy evolution? When did filaments begin feeding young galaxies in a way that changed their growth? When did protoclusters begin behaving like real environments instead of loose associations? When did the web move from invisible dark matter preference to visible galaxy geography? These are not philosophical questions. They can be tested, but not instantly. They require larger surveys, better redshifts, deeper spectroscopy, stronger lensing models, improved simulations, and careful comparison between observed populations and predicted ones. The next uncertainty is abundance. One surprising structure is not enough to rewrite cosmology. A few surprising structures may still be rare peaks. The crucial question is how many exist in a given volume of space and time. If early massive regions are as rare as lambda CDM predicts, then Webb may be revealing the expected extreme tail. If they are too common, then the pressure becomes harder to contain. Cosmology is not only a science of dramatic examples, it is a science of counts. Abundance turns wonder into statistics. How many massive galaxies should exist at a redshift? How many dense regions should appear in a survey field? How many strong lensing clusters should be found at early times? How many protoclusters should show environmental effects? Each answer depends on assumptions, but the population is where those assumptions are tested. The universe cannot hide forever behind one beautiful outlier. The next uncertainty is mass. Mass is not as simple as brightness. A galaxy can shine brightly because it is forming stars rapidly, not because it contains an enormous old stellar population. Dust can alter its colors. A burst of young stars can dominate the light. A cluster's total mass may be inferred from lensing, galaxy motions, hot gas, or models, and different methods can disagree. To say something is too massive too early, scientists must know how massive it truly is and how secure that estimate remains after better data arrives. Then there is concentration. A structure's total mass matters, but so does how that mass is distributed. A cluster with a dense core can bend light strongly. A high concentration may suggest early formation or unusual assembly history. But concentration depends on modeling, alignment, sample selection, and the details of dark matter halo growth. If early clusters appear more concentrated than expected, the question is not only how much mass exists, but how quickly it gathered toward the center. That question reaches into the dark. Visible galaxies can fool us, but gravity is harder to negotiate with. Lensing gives mass a way to speak without light. When background galaxies stretch into arcs, space-time has carried a message. Yet even lensing must be modeled. Astronomers have to identify which arcs belong to which background sources, estimate their redshifts, choose a mass distribution, and test whether the model reproduces the observed distortions. The evidence can be strong and still require humility. The next uncertainty is ordinary matter. Baryonic physics. The physics of gas, stars, dust, supernovae, and black holes is messy enough to shift interpretation. Dark matter may set the scaffolding, but ordinary matter determines what Webb actually sees. If early star formation was bursty, galaxies may appear temporarily overbright. If gas flows along filaments were efficient, dense regions may grow visible galaxies quickly. If feedback was weaker, delayed, or different in early environments, galaxies may become massive faster. If dust is abundant, colors may mislead first estimates. The model may not be broken. The visible recipes may be incomplete. This matters because the word physics contains many layers. There is fundamental physics, gravity, expansion, dark matter, energy, the initial conditions of the universe. Then there is astrophysics, gas cooling, star formation, feedback, mergers, dust, black holes, chemical enrichment. Attention in early structure may not mean the deepest laws are wrong, it may mean the astrophysical processes inside those laws are more extreme, more efficient, or more environment-dependent than expected. That is why the final boundary must be drawn carefully. Known. The universe forms a cosmic web. Known. Dark matter is essential to that web. Known. Webb is revealing early galaxies and environments with unprecedented infrared power. Likely. Some early dense regions are rare but physically allowed peaks. Possible. Some galaxy formation processes in dense early environments were faster or more efficient than models assumed. Uncertain. Whether the abundance, mass, concentration, and maturity of early structures will remain in tension after larger samples and better confirmations. Speculative. That fundamental physics must change. The honest story lives in the space between likely and uncertain. That space is not weak. It is alive. It is where future observations matter. More Webb fields, more spectroscopy, deeper surveys, better simulations, and comparisons with other telescopes will either soften the tension or sharpen it. If the pressure fades, science learns why the first image looked dramatic. If the pressure survives, science learns where the old description was too simple. Either way, the universe becomes clearer. This is why the title should not end with fear. A structure bigger than physics should allow is a doorway, not a verdict. Behind it is a more exact question. What does physics allow when dark matter begins early? Gas flows efficiently. Galaxies live inside dense environments, and our instruments finally become sensitive enough to see the process before it finishes. The final answer cannot be that the universe broke its rules. The final answer has to be more demanding. The universe may be obeying its rules with a precision we are only now learning how to measure. And the last step is to return to the darkness where the story began, now carrying the full weight of what Webb has made visible. The darkness is no longer empty. It may still look empty to us, because human sight is a small instrument built for a nearby world. We can stand beneath the night sky and feel space as distance, silence, and scattered light. We can look between the stars and imagine absence. But absence is not what Webb has been showing us. The blackness is full of relationships too faint for the eye, too stretched for ordinary cameras, too old for intuition, and too large for a body to feel. In that darkness, galaxies are not alone. They belong to threads. The threads belong to knots. The knots belong to a web whose roots reach back toward the first unevenness of the universe. What looked like a field of separate lights becomes a record of gravity choosing paths over billions of years. What looked like emptiness becomes structure. What looked like structure becomes memory. That is the final meaning of the title. James Webb did not find a single object that physics forbids. It found a deeper view of the kind of structure that forces physics to become specific. The word bigger is not only about length across space. It is about the size of the explanation required. A true cosmic structure is bigger than a photograph, bigger than a bright galaxy, bigger than one measurement, bigger than the first headline attached to it. It reaches into dark matter, gas cooling, redshift, lensing, star formation, feedback, simulations, statistics, and the first density differences after the beginning. Physics does not shrink from that. Physics becomes sharper there. The universe is allowed to build large things. It is allowed to form filaments, clusters, voids, and walls of galaxies. It is allowed to make rare peaks where matter gathers early and growth runs ahead of the average. It is allowed to surprise human expectation, because human expectation was never the law. The real test is whether our models can predict how often these structures appear, how massive they are, how concentrated they become, and how early they begin shaping galaxies. That is why Webb's discoveries matter, even when they do not break anything. A measurement does not have to destroy a theory to change science. Sometimes it changes science by narrowing the theory's hiding places. It says, not just any formation history will do, not just any gas recipe, not just any estimate of star formation efficiency, not just any assumption about environment. If early dense regions are real, common, and influential, then the model must explain them with the same honesty it uses to explain the cosmic microwave background, the expansion of space, and the web we see nearby. That is a difficult demand, and a beautiful one, because the best scientific discoveries do not leave us with chaos. They leave us with better questions. How quickly did the invisible scaffolding of dark matter become strong enough to guide the first galaxies? How soon did filaments become supply lines? How early did dense environments start changing the lives of the galaxies inside them? How many massive early nodes should the universe produce if our assumptions are right? Which apparent anomalies will fade with better measurements? And which will survive? The answer will not arrive all at once. It will arrive through more fields, more spectra, more lensing models, more simulations, more careful counts. A galaxy candidate will become confirmed, or move to a different distance. A dense region will become a protocluster, or dissolve into projection. A mass estimate will settle upward or downward. A rare object will become part of a known population, or remain too frequent for comfort. Slowly, the dramatic phrase becomes a scientific map, and that slow process is not a disappointment. It is the reason the story is real. There is something calming in the fact that the universe does not need our urgency. It has carried this structure for billions of years without explanation, without audience, without a name. The light Webb catches has already travelled across most of cosmic history. The galaxies in those images have already changed, merged, faded, or become part of structures we will never see as they are now. We are not watching the universe in real time. We are receiving old messages that arrive only now because space itself is large enough to delay them. A structure in a Webb field is therefore both present and gone. Present, because its light reaches the telescope now. Gone, because the scene has evolved during the light's journey. The galaxies are not frozen in the state we observe. Their descendants may now be part of larger clusters, quieter galaxies, richer environments, or structures far beyond our direct view. Every ancient image is a time capsule that opened late. That is why deep astronomy always carries a quiet sadness. We see things not when they are, but when their light finally reaches us. We learn the early universe from evidence that has survived distance. We build maps from photons that crossed expanding space long before there were eyes on Earth to receive them. And still, somehow, the pattern is strong enough to be read. The darkness was never empty. It was only waiting for the right eyes. That line is not poetry alone. It is almost a technical statement. To the eye, there is blackness. To an infrared telescope, there are galaxies. To a redshift catalogue, there is depth. To a density map, there is structure. To a lensing model, there is hidden mass. To a cosmologist, there is a test of growth. To a human being listening late at night, there is the strange recognition that reality contains order long before we are able to notice it. And that recognition changes the sky. The next time you look upward, the stars may still seem scattered. The spaces between them may still seem silent. Nothing in the familiar night will draw the cosmic web for you. No filament will glow across the sky. No cluster core will announce the dark matter holding it together. No ancient redshift will appear beside a faint point of light. Human vision will still see a simple darkness. But beneath that simplicity, the structure remains. Above you, around you, and through the region of space that contains our own galaxy, the universe is threaded by ancient gravitational history. The Milky Way is not outside the web. It is one small, luminous inhabitant of it. The matter in your body formed in stars, but the place those stars belong to was shaped by larger structures that began before stars like the Sun existed. We are not separate from the architecture Webb is revealing. We are late-born matter inside it. That may be the deepest afterimage. James Webb did not make the universe more frightening by finding something beyond physics. It made the universe more intimate by showing that the largest structures are connected to the smallest beginnings. A tiny density difference, almost nothing at first, can grow into a road for galaxies. A faint infrared smudge can reveal an environment. A stretched arc of light can expose invisible mass. A dark patch of sky can become a record of how the universe learned to gather itself. So perhaps the real structure bigger than physics should allow was never a forbidden object. It was the expectation that the universe should fit inside our simplest picture. Webb has not broken the rules. It has widened the frame around them. It has shown that the early universe was not a blank darkness waiting to become complex. It was already carrying the seeds of architecture, already leaning toward filaments and knots, already preparing places where galaxies would grow faster, burn brighter, and change sooner. The laws were there, the memory was there, the web was beginning. And in a patch of sky that once looked empty, the universe has finally let us see that it was building something all along.